Friends, we are now coming to module 2 for this course. Now, in module 1, I delivered 2 lectures essentially dealing with very briefly the history of non-ferrous metal production in India. In this second module, we are now coming to the subject proper and we will briefly discuss the following things: sources of non-ferrous metals, land and sea, principle of exploration of mineral deposits, principles of ore beneficiation, and when we discuss the sources of non-ferrous metals, we will definitely talk a bit about non-ferrous metal wealth of India. Now, you should first know very clearly the distinction between ore and mineral. Do not confuse these two words. An ore is a mixture of many minerals. Ores contain minerals, but the word mineral means is a naturally occurring inorganic compound containing one or more metals in association with non-metals such as oxygen, sulfur and halogens in more or less in a fixed composition. Like when you say hematite is a mineral of iron, hematite composition is Fe2O3. When we said some other mineral like galena, it is PbS, it is a mineral of lead. But in nature, very rarely you find a mineral as such. There will be many minerals mixed together, and along with them there will be other minerals which we normally do not associate as a source of metal, like sand, like aluminosilicates, which are part of sand. These we often call as gangue, or things that simply dilute the metallic value, but they are also minerals. So, a mineral is a naturally occurring inorganic compound, and it will be a combination between metal and a non-metal like oxygen or sulfur or halogens. Like you will find some exposed seabeds, some chloride deposits, which actually have come from the sea. After the sea water has vaporized from that shallow beaches, you are left with some salts which are chlorides. Even our salt mines, which is sodium chloride, it is a source of sodium, but very rarely it is only sodium chloride. It would have other chlorides in it. An ore therefore, may be defined as a naturally occurring aggregate or a combination of minerals from which one or more metals can be recovered. So, when we say here we have an ore, which means we can get from that ore 1, 2, 3, maybe more metals, and there are processes available for that. But just you may have something, it does not become an ore. For example, you go somewhere where there is a whole lot of sand there, in theory it has SiO2, in theory you can get silicon out of that, but we do not call it an ore of silicon. Obviously, something that is not considered an ore today may become so tomorrow when technology advances, like the sand would become an ore of silicon if there is a technology which can economically or efficiently get silicon out of that. Or or when you have clay, all kinds of clay which has alumina in them, we can consider someday it can become an ore of aluminum, but today it is not an ore of aluminum. Now, where do we find these minerals? There are ores and minerals on land, and we say that they are found in earth's crust. Now, we cannot dig into the earth, because people know that the core of earth is very rich in heavy metals like nickel, iron, etc. But we cannot get there. Our explorations for metals are generally confined to a few kilometers of the earth's surface, and we can call it a crust, maybe 10 kilometer thickness of the earth, that includes the sea, mind you. That is called a crust. So, the land area in that crust is a source of ores and minerals. And there is also the sea, which is the largest part of the crust. The sea also is a source of metals, because there are many minerals have deposited in them. We find that for various geochemical processes, not all elements are found everywhere. Means elements that make this earth is not uniformly distributed, at least in the crust. There are reasons why there are pockets of some available here, pockets of some other metals are available elsewhere. Normally, in flat grounds, you will find deposits of alumina, aluminosilicates. In hilly region, especially hills that have been weathered away, like the Aravalli region of Rajasthan, you find sulfides. There are various reasons why you get sulfides in this kind of region and oxides in flat ground. I would not go into that. But the point is that not all metals elements are uniformly distributed. Now, suppose you find there is an ore, and I mentioned something which is not an ore today may become an ore tomorrow, but what really makes an ore that is governed by technology and economy. And here are the points. First of all, the percentage of metal values has to be reasonably high. If suppose there is an ore where the metal value is very small, then we would not like to call it an ore. In India, for example, we have iron ores which are very rich in iron. There are also ores which are so poor in iron that we do not consider to be iron ore in India. But for some other country, it could be an iron ore, because they do not have ores even containing that much of iron. So, percentage of metal values in an ore is an parameter. Nature of the occurrence, that is form of occurrence, it may be high in a metal, but it may be so fixed with the other non-metals or gangue materials that it is very difficult to get it out of that ore. So, again we will not call it an ore unless the metal value is recoverable. That is related to percentage of impurities and their association. Physical conditioning of the ore. There are in some areas iron ore which is very pure, but it may be found in a fine form. It is very difficult to process such an ore. We may not call it an ore. Then there is also location and magnitude of deposits. If it is located in a very odd place, which is very hard to for transport, or the deposit is very small, it may not be attractive from economical point of view. proximity to transport facilities and other services. Suppose in the Himalayan range you find some ore bodies. Well, it may be good from theoretical point of view, but practical point of view we cannot exploit them. So, we would not consider it to be ore. Market value of metals. If an ore has metals, maybe high values, but the metal value is negligible, then it is not much of an ore. Then the economy of extraction, which we are discussing, would also relate to two other things: value of land, cost of rehabilitation. If it becomes very difficult to acquire land in a place for whatever reasons, if there are people being displaced, the cost of rehabilitation is very high, then the factors that govern economy of extraction would be negative. That should rather not go for putting up an industry for extraction. Similarly, there are other issues like environmental and social concerns. If we have a process that will cause too much of pollution in an area where there are people all around and their lives will be affected, then we will not have a good practical reasons for going for extraction. So, as I said that a whole lot of factors govern the economy of extraction, and they have to be came in time. Now, how do we find such ores and minerals? Now, in ancient times it was easy because many minerals were easily spotted on earth's crust. Even now you go to many areas, you find red earth, you know it is iron ore rich. You might even get big boulders of iron ore, hematite lying around. Similarly, many other minerals are easily spotted and people had understood that what metals were contained in them, because the physical characteristics made it very apparent as to what kind of metals were to be found in them. But then as the extraction processes became more sophisticated and the demands for very large ore deposits were there, because you wanted to set up industries, modern methods had to come for exploration and identification of ore bodies, many of which were hidden under the earth and many of them were not apparent on the surface, because in ancient times they were all on the ground. So, our ancients had taken them out from the surface, have already processed, and the millennia have passed and everything is full of soil. Hidden under the soil are the ores. How do you find what are they? Now, for that we apply geophysical methods. We try to understand the properties of the layers of earth in that area. Now, of course, if we suspect that there is something in certain area, we have to make some measurements. There are geophysical measurements and surveys are done on the surface to understand how the electrical property is changing, how electrical resistivity is changing. If these things change, then we know there is something under the surface. Suppose there are radioactive minerals, then radioactivity will change as you go by. So, we have to depend on geophysical measurements for exploration. So, that is the first step. After you have suspected through geophysical explorations the occurrence of some ore bodies, then you have to go for actual drilling, and by drilling and taking out samples. Now, this sort of thing is outside the scope of this course, but I just want to give you a hint of the way things perhaps are done. Now, here is an example of trying to locate some magnetic ores. You know, there are many ores which are magnetic, properties, like for example, some ores of iron ore, I mean ilmenite is magnetic. There are others, and as we go by we will see some of them. So, suppose this is the layer surface and this is a soil layer, and hidden inside is a magnetic ore body. Now, on that, if a survey is done and magnetic measurements are made in two directions, this way and that way, from that one can draw a map of something that is hidden below the surface, which is giving anomalies in measurements, magnetic measurements. Similarly, if one applies a voltage at different locations and measures the current flowing, and they find that there is some place where resistivity is suddenly dropping. Means you find you go on measuring the current flowing and take the whole thing from one place to another, and you find there is a place where suddenly there is a hint of drop in resistivity, means the whole thing seems to be very conducting, there is something under the surface. Then you suspect there is hidden inside a ore body which is electrically conducting. So, then you have to start drilling here, find out whether your suspicions are true. Similarly, there are electrical flow line survey can be done in different directions. They find the current lines, they find equipotential lines, and from them they can actually guess the kind of ore body, shape and size of the ore body that is under the layer of soil. Now, these days the measurements have become so sophisticated that they need not go and do the survey on ground, it can be done from aircrafts. So, the aircrafts fly on the ground in a grid form in this direction first with certain intervals, and the plane will fly in certain direction in other directions, and they will maps will be drawn of electrical, magnetical and all kinds of properties, from which they can guess that where this is what kind of ore body may be there. Now, I will not discuss anything beyond this. I will now go into the subject by starting with sources of metals. For more details of this, you can refer to my book, to which I made a mention earlier, Extraction of Non-ferrous Metals, Ray, Sridhar and Abraham, and is published by affiliated East West Press Limited, first published in 1984, but then it is being repeated many times. Now, many figures and tables that I will show will have a reference for which the details are given in this book. So, I have not given details of all the references in the diagrams etc., that are showing. For that you have to go back to that book. Now, as I mentioned earlier, there are ore deposits all over the earth's crust, all over the globe, but there are certain pockets which happen to be very rich. It is true also country wise, like in India, there are certain pockets in the south of Bihar, Jharkhand area or Salem in Tamil Nadu, they seem to be extremely rich in certain elements. Similarly, in the coastal areas, there are certain areas we are very, very rich in certain things. I would not go why this has happened, but this is the fact that there are pockets where they are rich in certain metals. What about the earth overall? Here is a table that shows the relative abundance of various elements in earth's crust. Mind you, again I am talking about the top layer of the globe, about 10 kilometer layer. We are not talking the entire cross section. I am not saying the earth is made up of this, no, it is talking about the crust. You will find that most abundant is oxygen. the oxygen of course is there in air, but oxygen tremendous amounts in all these silicates, silica, alumina, they are all made of oxides. Then the element which is the most abundant is silicon, then comes aluminum, then comes iron. Now, you will find ours is an iron age. So, you would think that iron is most abundant metal, which is not true. Aluminum is more abundant than iron, but why is iron more popular? It is because of its properties, because it is easier to extract. Iron has been extracted long ago, because iron oxide can be reduced by carbon, either charcoal or coke. Alumina cannot be produced that way. For aluminum to be produced, one had to wait till the 18th century and invention of electricity. Without that, it was just not possible to produce aluminum in large scale. As a matter of fact, even in the 18th century and rather 19th century, towards the middle, a little later when aluminum was just beginning to come, it was so expensive that many kings served fellow kings food on aluminum vessels, on aluminum plates with aluminum cutlery, because it was much more expensive than gold and silver. But you find that aluminum, in spite of its abundance, is not as common as iron. Now, if we take the first 8 metals in the list, the first 8 metals make 90%, means from oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, up to here, that is 98% of the earth's crust, and of this 75% is accounted for by only silicon and aluminum. The rest are all in very small quantities. So, again the use of a metal in every day is not related to the relative abundance in earth's crust, because there are many factors which govern why a metal should become popular: economy of extraction, its properties, and based on that only iron has become so important. Aluminum is also becoming important. Now, apart from the earth's crust, the land mass, the other source of non-ferrous metals is the seas. The 7 seas, as we say, they cover the globe. Now, since water flows everywhere, you may think that the composition of sea water should be uniform. This is largely true, but there may be reasons why there could be certain locations where the seawater composition is bit different from seawater composition elsewhere. You must try to understand what has given these metals in the sea. Now, one theory is that over the millennia, the rivers that are flowing over land, that are coming from the hills, they have dissolved. Through dissolution, they have brought in many elements and which have gone into the sea, or they have caused erosion of many minerals which have gone into the sea, and through some reactions have dissolved in the sea. But if we have to find something in the sea, obviously it is something which is in the soluble state. We will see later on in the sea, there are also some insoluble matter which are sources of metals. But this theory does not account for all the dissolved elements in the sea. It is now known that the elements in the sea are not only coming because of the rivers flowing into the sea, or the rainwater washing material from land mass into the sea, but some are coming from the bottom of the sea, because there are many sea bottoms have big cracks which run for kilometers and hundreds of kilometers. There are undersea volcanoes, and from there are eruptions. There are continuous inflow of various things which contain different kinds of metals. So, that is undersea input of elements as well as the inputs from rivers, etc., that account from the elements that we find in the sea. Now, in the sea, everything, every element you can think of is present. Now, interestingly, of course, the most abundant is chlorine and sodium, because sodium chloride dissolves in water, and you would not find sodium chloride on land if they had been, it has all been washed down. So, these two are maximum. Then comes magnesium, magnesium chloride is there, then there are all other things are there. In fact, you will be surprised to note that there is also gold and silver in seawater. You will see there is gold also. Now, you might think this gold in 0.000004 to 0.000008 means nothing, but that is not true. We are giving them here in gram per ton. Now, if you find out 1 cubic kilometer of seawater, find out how many tons that means of seawater, and if you multiply by this gram per ton, you will find that will mean huge amounts of gold. So, if we could get hold of 1 kilometer cube of seawater, we can extract a lot of gold from that. And in fact, attempts were made to extract gold from seawater at one time, I think somewhere in France, sea beach, but they had to abandon that because it was feasible, technologically possible, but not economically attractive. Means you had to process huge amounts of seawater to get that gold, which is not worth all that expenses. So, what I am saying is seawater has all these things, whole lot of things in seawater. They are in solution, in some salt form. Now, apart from that, we know that all these dissolved salts account for 3.5% of dissolved solids that seawater contains. Most seawater has 3.5% dissolved solids, and in that 3.5% all these elements are there. Notice one important thing, the relative abundances of elements in seawater are very different from the relative abundance figures in the land mass. It should be very clear to you why it is, because here it depends on solubilities. What is more soluble in water will be present in greater amounts, and also what is coming more from the bottom of the sea will be in greater amounts. So, seawater has one kind of distribution of elements and the land mass has another kind of distribution. Now, as I said, there are localized changes because of injection from the bottom of the sea, and there is also another very interesting reason why there are certain regions, pockets, where the elemental concentration can be different. And this comes from sea organisms absorbing certain elements in preference to others. It is known that some sea organisms like algae, they accumulate, it is a kind of seaweed, they accumulate high concentrations of iodine. In fact, iodine as an element was first found from analysis of algae. So, if there is a region of sea water where there is a lot of algae, you will find lot of iodine in that part of the sea. Algae is not found everywhere in equal amounts. So, iodine will be concentrated there. There could be other such organisms or even some animals which actually selectively accumulate certain elements. So, apart from the sea water as a body, we also consider the sea organisms as source of elements. So, the sea is giving us two sources, the sea water and the sea organisms. There is a third source in sea, which is very interesting. They are called polymetallic nodules or manganese nodules. In the floors of many seas, and that fortunately includes also Bay of Bengal, people have found rounded solid nodules from say half a centimeter to couple of centimeters, 10 centimeters, 12 centimeters. They cover seabeds, huge areas, and people have analyzed to find that these nodules are very rich in some elements, some metals. That is why they are called polymetallic nodules. And this is an estimate of reserves of polymetallic nodules, or I am writing reserves of metals in Pacific Ocean nodules, and I am comparing them compared to land reserves and nodule reserves. Now, it is surprising that there are the nodule reserves apparently contain 5,000 times cobalt than is available in land reserves. In the case of manganese, 4,000 times than that in the land reserves. Nickel 1500 times, and etcetera, etcetera. Now, a lot of interest now has grown in this area, and there are all kinds of international treaties regarding sea coastline, sea floor, and essentially if you want to be in the game, you have to spend money. You must understand why India sends an expedition to Antarctica every year, because we have a permanent station in Antarctica. We claim a part of Antarctica. Similarly, in sea water, in the sea floor, countries which invest money in explorations are given rights of extraction of nodules. So, India is amongst a few countries which have invested heavily in survey of sea floor to see how much of nodule is available where, and then finally, India has settled for certain areas and said they are not interested in other areas. So, they have let go their rights to the other areas, but in the Bay of Bengal and some other places, India has spent money and they have rights of excavations of sea nodules from that area. There is a problem, because the sea nodules are in the ocean floor. To get them out of that ocean floor in large quantities is difficult, but in future we may have a technology of pumping them out, or some undersea vessels going there and mining them and bringing them out. There are also some shallow seas, like not far off from the shore in Bay of Bengal, where sea nodules are found. That may not be so difficult. In Pacific Ocean, you have to go 5 kilometers down below to the sea floor to get the sea nodules. Anyway, coming back to the subject, the Pacific Ocean nodules figures are only for Pacific Ocean. It does not mean other oceans do not have it, they also have that. Now, we have talked about 4 sources: the land reserves, the sea, and the sea means in the sea we have the sea water, We have the sea organisms like the weeds. We also have the ocean floor nodules. There are two other kinds of sources, and to that I would come later. Let me first mention one or two things about the land reserves. In our book, we have given a lot of data about what minerals are found everywhere, which country is rich in which ore and which mineral, but it is not necessary for you to know this. If you get some time or if the occasion demands, you can go through. But I wish to point out the worldwide distribution of some important metals to indicate where does India figure, because there are a few places where India is very important country. Manganese, you will find there are some countries like South Africa or USSR, most of the manganese found there, but manganese is found in India also, large quantities, at least enough for now. Cobalt, you will find Zambia, Zaire have almost 50% of world's high grade reserves. South Africa, Zimbabwe has 97% of the high grade ores of chromium. Aluminum is where you will find mention of India. India has large deposits of aluminum ores, maybe not as much as some other countries like Brazil or Jamaica or Canada, but it is fairly large. Tin, China has 24% of world reserves, India has nothing, very little tin, only some tin has been found in Madhya Pradesh, Bastar district. Unfortunate. Antimony, we do not figure anywhere. Tungsten, we do not figure in the list of countries which are rich. Iron ore, India comes there. We have only 6% of iron ore, but we have high quality iron ore. Uranium, we do not have, and that is the big problem with India and all the nuclear treaty etc., is to look for this uranium from Canada or USA or Australia or South Africa who have uranium ores. Copper, we have some, but we are nowhere amongst the countries which are rich. Same with molybdenum, columbium. India figures very strongly in titanium. We have titanium 4%, I should not say very strongly, but fairly strongly 4%, and something that is not mentioned, India is very rich is in thorium. I will come to that later on. So, to summarize actually India's, we can say that about the mineral wealth of India, we have adequate to abundant ores, aluminum, beryllium, chromium, manganese, magnesium, titanium, zirconium, thorium and the rare earths. Inadequate but present ores of copper, gold, graphite, it is not a non-metal, but I have included it here, lead, vanadium, zinc, cadmium, nickel, uranium, tin. Poor to not so far unknown as ores of antimony, bismuth, boron, cobalt, mercury, molybdenum, niobium, tantalum, etc., etc. Here we have included some non-ferrous, non-metals also. Now, the supposition of India is not very rich in terms of non-ferrous metals, excepting thorium. We do have adequate quantities of titanium, manganese, zirconium, etc. But what we have is our expertise. It is not necessary always to have your own ores and minerals. If you have the intelligence, you can import, process and have your metals and minerals. Look at Japan, they have no minerals, they have no ores, but they have the knowledge, they have the technology and they have the right policies and they thrive. So, we need not always say that we cannot be rich in this area of technology because we do not have the ores and minerals, it is not necessary. But certainly, ores and minerals give you the mineral wealth. From that, India is not as well placed as South Africa or Australia or America or Canada, but not very poorly off also. You should know that at one time India was the only country which produced diamonds in South India, Golconda. All the diamonds came out of Golconda until the South African mines were discovered in the last century. Now, they are the leaders. Nobody knows. It is quite possible that there are somewhere hidden here and there some mineral wealth we still have not found, and we will find them. It is possible. So, the exploration is very important for India. So far, what I have discussed is that what are the sources of metals, and I have pointed out that the important sources of land mass, sea water, and in sea water, in sea you have sea water, sea organisms and nodules. There is one more source of metals that you should not forget, and that is scrap metal. And metals that are recovered from metal scrap or wastes are known as secondary metals. Like supposing we are producing aluminum and we are sending it out into the market in the form of vessels or containers, etc., which after some time are discarded. That becomes a source of the metal that has to be recycled. Like iron and steel, in the advanced countries, some 40% of iron comes from recycled iron, and many of them come from car bodies. Lead can be easily recycled, aluminum, zinc, copper, everything can be recycled. And when you recycle the metal, there is an advantage that it needs much more energy to extract the metal from ore. It requires less energy to extract it from scrap or some metallurgical waste, which is not a metal scrap, but maybe it is there in the slag, you recover it from there. It will require less energy and they will be less expensive. Actually, you can think of a day where the world will not need ores and minerals. The world will produce all the metals it needs by recycling the scrap, because after all you cannot go on producing more and more and more and metals for all kinds of uses. There will be a saturation point that you do not need more than this much of metal at a time, and you have a steady state. The scrap that goes comes back and you produce the fresh metal. It is beginning to happen, as I said, in Western countries. For iron and steel, about 30-40% is being recycled. So, scrap metal is also a very important source of metal, and there is also something called metallurgical wastes. In many metallurgical processes, we may produce a slag which contains a valuable metal, and perhaps the slag is a better source of the metal than some ore on the surface of the earth, on the land mass. There are, we will see examples that in many cases it is from the slag we recover that metal. So, slag is a metallurgical waste, there can be other kinds of wastes. So, metallurgical wastes and scrap metal is another source of metal. Now, I just want to end this by mentioning one more thing. That we talked about manganese nodules, and I said that there is much more manganese in them, much more of something than we have in the sea. and I said there is a problem that to get them out of the sea floor is a problem. There is another problem. Say there is a whole lot of manganese in the manganese nodules, which are actually polymetallic nodules, but there is manganese available in Earth's crust also as manganese source, and it is easier to get manganese out of that. It is something that gives a negative picture to that nodules, that we need not extract nodules for manganese, but we have to extract them for the other metals like nickel, cobalt, etc. But then we have to end up extracting manganese also. So, it is a question of economics. You cannot take out just one or two metals from a nodule that you have taken so much effort to bring it out of the sea floor. But then if you take out all the metals, that including manganese, it is also not very advisable, because there is a lot of manganese on Earth's crust which is very easily extracted. So, a lot of conflicting things are there, but on the whole manganese nodules can be called a future source of some strategic metals. And interesting things about these nodules, which average size, as I said, from this to that about 4 centimeter, is that they are being produced all the time by some processes in the sea floor, and it is said that everywhere some processes occur where maybe some sea organisms also take place, and they have said that in the Pacific Ocean alone, the estimate is every year 10 million tons of these manganese nodules are produced. Now, in a land mass, if there is an ore body, it is fixed, it is not renewable, but manganese nodules appear to be renewable. You can take them out, again fresh amounts of needle will be found. Actually, people have done experiments to find this out. They have taken out some manganese nodules from some areas and have seen the fresh generation of manganese polymetallic nodules. So, we have an inexhaustive source of nickel, cobalt, copper and manganese and some other materials also. If only we could get them out of the sea floor, we will have no problem. And I mentioned that India may not be very rich, but then we are not very poor either. I like to end by mentioning one particular, I do not have a slide, I will show you this particular table, not this table, sorry. Maybe I will cover that in the next. I like to talk about in the next lecture a very particular resource that is very important for India, and that is all along the sea beaches we have a special kind of sand in certain pockets, which contain many minerals, not only titanium, but rare earths, and that is a very rich raw material we have, and I will discuss that in the next lecture. So, let me wind up by saying that we have discussed briefly from where do we get metals, what is the difference between an ore and a mineral. We cannot call any source which has metal an ore, because there are some economical factors that tell us whether we can extract metal out of that body. There are also technological factors that unless we have a process to extract the metal out of an ore body, we cannot call it an ore. Like the question can be, are manganese nodules ores of nickel and cobalt? we do not use the word ores for manganese nodules yet so very easily. We say they are sources of several metals, they are sources. They will become ores when we will have an economical method of extracting, of taking them out of the sea floor and extracting metals. Incidentally, many CSIR laboratories have worked on this polymetallic nodules from sea floor. I happen to be the director of Regional Research Laboratory Bhubaneswar, where we have a project which is going for about 20 years on extraction of these values from manganese nodules or polymetallic nodules from the sea floor. Our job is to extract the metallic values from the nodules given to us. Some other agencies' job was to collect them from the sea floor. Now, we have a process, not only us, there is another laboratory which has also worked on the process. We believe that we are technologically successful. We can get all the metals out by a process which someday can be scaled up, and there can be plant operating which will produce these metals, starting with these polymetallic nodules from the sea floor. The question of economics is mostly tied up with extraction, with collection from the sea floor. If that can be solved, we will have a process, and if that could be done, India will have all the cobalt and nickel it wants, and also some other metals. Some people have argued that you have to take out manganese also, but maybe we will take out manganese as well. So, thank you very much. Now, in the next class, I will talk specially about the beach sands of India, one of the most important resources we have that contain titanium, thorium, rare earths and these valuable things. It is very important from the point of view of our nuclear energy program, because it has to be based on thorium. So, our next lecture will be on beach sands, particularly how do we treat them, how do we beneficiate them, and how we extract things from them. Thank you very much.